All right, welcome back. Today we're diving into something pretty exciting in generative AI.
Yeah, it tackles a fundamental question. With latent diffusion models, LDMs, we usually train them in two steps.
Right, first you train the VAE, the Variational auto-encoder, to compress images into that latent space.
And then you freeze it, totally freeze the VAE, and then train the diffusion model to generate stuff within that fixed space.
But the question's always been there. Wouldn't it be better, potentially, to train both the VAE and the LDM together, end to end?
Intuitively, yes. But the problem is, trying that the straightforward way, well, it just hasn't worked. It tends to mess things up.
Yeah, it leads to what they call latent space collapse and actually worse image quality, kind of the opposite of what you'd hope for.
Exactly, and that's the core problem this paper tackles. It's called REPA-E, Unlocking VAE for End-to-End Tuning with Latent Diffusion Transformers by Lang and colleagues.
REPA-E, okay.
And they figured out why just backpropagating the normal diffusion loss into the VAE fails. Their big contribution is this new training recipe, REPA-E.
Built around something called representation alignment loss.
That's the key. And it finally makes this end-to-end tuning actually work, and work well.
Okay, so how does it manage that? What's the secret sauce here? Because, like you said, the simple approach fails.
Well, the core idea is, instead of using that standard diffusion loss to train both parts, they shift the focus.
Yep.
They concentrate on aligning the internal workings, the representations, inside the diffusion model.
Aligning them with what?
With the representations from a really powerful, pre-trained visual encoder model. Think of it like making the diffusion model see things in a similar way to a model that's already great at understanding images.
Interesting. So for everyone just tuning in for the quick summary, trying to train LDMs and VAEs end-to-end the old way doesn't work. Latent space collapses.
Right. This new method, REPA-E, uses this representation alignment idea instead. And it does work.
And the results are pretty dramatic, right? Like massive training speedups.
Huge. They're talking 17 to 45 times faster training to reach comparable or even better quality.
Wow. And it doesn't just speed things up, it actually improves the VAE itself too, making the latent space better.
Yeah, exactly. Better structure in the latent space, which helps downstream generation. And it sets a new state-of-the-art score on ImageNet 256 by 2556 and FID of just 1.26 using classifier-free guidance.
Okay, that's seriously impressive. So our mission for this deep dive is to really get into the weeds of REPA-E. Understand the mechanics, the why, the how.
Yeah.
Basically, figure out why it's such a potential game changer.
Sounds good. Let's maybe start by quickly recapping that traditional two-stage process, just so we're all on the same page. Figure 1A in the paper shows it nicely.
Stage 1, train the VAE. Get it good at encoding images down into that latent space and then decoding them back, using standard stuff like reconstruction loss.
Right, squared error,
Yep.
LPIPS for perceptual quality. Maybe a Jan laws, the KL divergence thing to keep the latent space behaving.
Yeah.
The goal is just good compression and reconstruction.
Then stage 2, lock down that VAE. Freeze its weights completely.
Yep. And then you bring in the diffusion model, often a transformer like SIFT these days, and train it purely within that fixed latent space.
Teaching it to basically reverse noise, right?
Yeah.
Start with noise in the latent space and gradually denoise it back into a coherent representation that the VAE can then decode into an image.
Exactly. And that's worked. Obviously, it's powered models like Stable Diffusion, but it has this built-in limitation.
The optimization challenge they mentioned?
Yeah. How do you know that latent space, which was only optimized for reconstruction, is actually the best possible space for the diffusion model to work in?
Right. There's no direct signal from the diffusion process back to the VAE saying, hey, maybe tweak this representation a bit. It would help me generate better images.
Precisely. It's like designing that puzzle piece, as you said, without knowing the exact whole shape.
And they point to real-world issues with these VAEs trained in isolation, don't they? Like the SDVAE having high-frequency noise sometimes, or others being maybe too smooth. Figures 2 and 6 show that variation.
Yeah, different VAEs, different latent space characteristics. So the obvious next step seems to be, well, just connect them, train them together.
Let the gradients flow. Take that diffusion loss from stage 2 and just backpropagate it all the way through the VAE too. Figure 1B shows that idea.
Seems logical. Let gradient descent figure out the optimal joint solution for generation.
And it fails spectacularly. Section 3, Table 1, Figure 1D, the results are clear. Performance gets worse. Why? What goes wrong?
It's a really neat insight they have. Section 3.1 explains it, and Figure 3A helps visualize it. When you push that diffusion loss back into the VAE,
Yeah.
it actually encourages the VAE to create a simpler latent space. specifically one with lower spatial variance, less detail across the latent channel.
Simpler how? Does that make the diffusion part easier?
In a way, yes, but not a good way. Think about the diffusion model's job. Predict the noise added at each step. If the latent space from the VAE has less inherent structure, less spatial detail, then the denoising task becomes less about understanding complex patterns and more about just predicting, like an average value or a biased term to subtract. The paper uses that exact analogy.
Okay. So the VAE learns to make the denoising task superficially easy, but it does so by throwing away the detailed information needed to actually generate good, complex images later on, optimizing for the wrong thing.
You got it. It's a path of least resistance that leads to a worse outcome. And this is where representation alignment comes in as the alternative.
Okay, so this is the core idea of REPA-E. What is representation alignment exactly?
They found, building on some prior work too, that there's a strong link. Figure 3b shows this, between how well the internal features of the diffusion model align with meaningful visual features from a separate powerful vision model, and the final quality of the generated images.
So you compare the diffusion model's intermediate processing steps to how something like, say, Dino V2 represents the original clean image.
Exactly. They often use Dino V2. The idea is, if your diffusion model starts to represent visual information internally in a way that mirrors how a really good vision model does it, it's probably learning useful, semantically rich features.
And they measure this using CKNNA scores.
Yeah, CKNNA is just a specific mathematical way to quantify how similar the representations are between these two networks. Higher score means better alignment.
Makes sense. Train the diffusion model to have good visual intuition by comparing it to a known good visual expert. So how does this help with that VAE bottleneck problem?
Right, remember how the fixed VAE limited things? Figure 3c illustrates this. If you just try to align the diffusion model's features with both the fixed VAE output and the Dino V2 features, like in the original REPA method, you hit a ceiling. The quality of the alignment you can achieve gets stuck, limited by how good those frozen VAE features are. The VAE just isn't giving the diffusion model the best possible starting point for high alignment.
Okay. The diffusion model is trying its best to match Dino V2, but it's hampered by the input it gets from the VAE, which wasn't optimized for this alignment task.
Precisely. And that's the breakthrough of REPA-E. They said, okay, let's backpropagate this alignment loss, the REPA loss, not just to the diffusion model, but all the way back to the VAE too.
So the VAE learns to produce latent features that are specifically designed to help the diffusion model achieve better alignment with that external vision expert, like Dino V2.
Exactly. It breaks through that bottleneck. The alignment score acts as a proxy for final generation quality, guiding the entire system, VAE and LDM end to end.
Okay, that's the core concept. Very clever. Now, how do they actually implement this? There must be some important details to make it work.
Oh, definitely. Several key components. First off, look at figure 1c. They stick a batch norm layer right between the VAE output and the LDM input.
Right. Usually you'd normalize the VAE latens using stats calculated over the whole data set, right? Why doesn't that work here?
Because the VAE is changing during training. Its output distribution is constantly shifting. Using fixed, pre-calculated stats would be inaccurate almost immediately.
Okay. So the batch norm calculates mean and variance on the fly for each mini batch.
Yep. And they use an exponential moving average, EMA, of those stats too, to get a more stable estimate over time. It's a normalization that can keep up with the learning VAE, and it's differentiable, which is crucial for end-to-end training.
Makes sense. Dynamic normalization. What about the alignment loss itself, LREPA? How's that set up?
So mathematically, it's basically the negative cosine similarity between feature patches. You take features from the clean input image using your pre-trained model, like Dino V2.
Got it.
And you compare those to features from an intermediate layer inside the diffusion transformer they mentioned, using the 8th layer of their CIDL-T model after passing them through a small learnable projection layer.
And the goal is to make the cosine similarity high. Make the features point in the same direction, essentially.
Exactly. Maximize similarity, maximize alignment. They also have these coefficients, lambda REPA-G and lambda REPA-V, to control how strongly this loss updates the diffusion model versus the VAE. Lets you balance the updates.
Okay, but you said earlier they still use the standard diffusion loss, LVIFF. How does that work without causing the latent collapse problem?
This is super important. They use a stop gradient.
Stop gradient.
Yeah. On the diffusion loss term, this means the diffusion loss only calculates gradients for updating the diffusion model parameters, theta. Those gradients are explicitly blocked from flowing back into the VAE parameters fight.
Whoa, okay. So the diffusion loss still trains the LDM to be a good denoiser,
Yep.
but it's prevented from messing up the VAE while the VAE is trying to learn better representations based on the alignment loss?
Exactly. It's a really neat trick. The LDM learns its denoising job, the VAE learns better representations via alignment, and they don't interfere negatively.
That's elegant. So is the VAE only learning from the alignment loss then, or does it still need to be good at reconstruction?
Good point. No, they keep the VAE grounded. They include standard VAE regularization losses, called LRA.
Like the original MSE, LPPS, maybe Jan loss, KL divergence.
All that stuff. These ensure the VAE doesn't forget its main job, reconstructing images faithfully. You still need good reconstruction quality, measured by RFID, for the final output to look good.
So it's a balancing act. RPAE loss pushes the VAE towards features good for alignment,
while the regularization losses make sure it still does good reconstructions.
Okay. And the overall loss function is just a weighted sum of all these parts. Diffusion loss for LDM, RPAE loss for both, regularization for VAE.
Precisely. L equals LDIFF plus lambda LRB plus eta LREG, applying each to the right parts. They also give the optimization details atom W, constant learning rate, batch size 256, gradient clipping, EMA on weights, run on 8H100s. Pretty standard high-end setup.
Got it. So that's the machinery. Now the payoff. Section 4.2, the results on training speed and performance. Table 2 looks pretty convincing.
Yeah, it really is. They compare REPA-E directly against baselines, including the original REPA-E, on ImageNet 256 by 256 without CFG using their big SciTXL model.
And the speedup is massive.
Huge. REPA-E gets way better FID scores, way faster. Like after only 20 training epochs, its GFID is already much better than baseline REPA-E.
Yeah.
By 80 epochs, REPA-E beats models like FasterDite, MaskDite, DDIT, SIT that were trained for way longer. Like millions of steps sometimes.
That's insane acceleration. And the final quality is better too, not just faster.
Significantly better. REPA-E hits an FID of 4.07 in just 400K steps. Compare that to the original RPA needing 4 million steps to get an FID of 5.9.
Wow, 10x fewer steps for a much better score. That's a game changer for training efficiency.
And you can see it visually too. Figure 4 shows images. Even early on, like 50K or 100K steps, the REPA generations just look more coherent, more detailed than REPA at similar points.
Okay, impressive speed and quality, but does it generalize? Section 4.3 looks at scalability and robustness, right, across different models, different settings.
Absolutely crucial question. First, model size. Table 3 shows SDB, STL, SDSL.
And REPA-E helps across the board.
Consistently beats vanilla RBA. And interestingly, the percentage improvement from REPA-E actually gets bigger with the larger models. That suggests it scales really well.
That's great news for future, even bigger models. What about the alignment target? Does it matter which pre-trained vision model you use? Table 4?
They tried a few IJEPA, Clippy, different Dynov2s. And again, REPA-E consistently gained improvements over REPA regardless of the specific encoder. Seems the core idea is robust.
Okay. And different VAEs, like SDVAE versus others. Table 5.
Same story. SDVE, NVE, VA. REPA-E improved generation performance across these different VAE architectures with their different latent space styles. Very versatile.
They even tried aligning at different layers inside the diffusion model. Table 6, layers 6, 8, 10.
Yep, and consistent gains there too. Doesn't seem super sensitive to the exact alignment depth.
And the Eblation Study in Table 7 really drives home how important each piece is, doesn't it?
Oh yeah. Take out the stop gradient, training fails completely, ditch the batch norm, performance tanks, remove the VAE regularization, reconstruction quality drops, herding generation. Every piece matters.
Maybe the most interesting result for me anyway is in Table 8, training from scratch. Both VAE and LDM together.
Right, this is huge. They show that while starting with a pre-trained VAE helps a bit, REPA-E can actually train both from random initialization end to end.
And even training from scratch, it beats the original RPA method, which needs a pre-trained VAE.
Comfortably. REPA-E from scratch at 400K steps beats REPA with its pre-trained VAE at 4 million steps. That really shows the power of this joint optimization.
Incredible. Okay, so it speeds up training, improves LDM performance, generalizes well, but what about the VAE itself?
Yeah.
Section 4.4 looks at how REPA-E affects the VAE.
Yeah, it's not just about the LDM. Figure 6 uses PCA to visualize the latent spaces. It shows REPA-E kind of cleans up the noise in SDVAE's latent space. And for VAE, which can be overly smooth, REPA-E seems to add back some useful detail and structure. So it adaptively refines the VAE's representation.
And that improved latent space actually helps downstream, Table 9.
Definitely. They took these REPA-E-tuned VAEs, they call them E2E VAEs, froze them, and then trained a standard LDM on top. And those E2E VAEs led to better LDM performance than using the original VAEs, even if they used a different LDM architecture for that second stage training. Shows the learned latent space is genuinely better and transferable.
Wow. So it improves the VAE in a way that's beneficial even your standard training later.
Exactly. Which all leads to the final headline results in Table 10. New state-of-the-art FIDs on ImageNet 256.
That 1.26 FID with CFG and 1.83 without. Plus, even the VAE reconstruction FID improves to 0.28. Just really strong numbers across the board.
Yeah, it clearly pushes the state-of-the-art forward thanks to this REPA-E approach.
Okay, so let's quickly recap the big takeaways. REPA-E successfully makes end-to-end training of VAEs and LDMs work
by using representation alignment loss instead of just the diffusion loss to guide the VAE.
Which avoids latent collapse, massively speeds up training, and improves final image quality.
Plus, it actually makes the VAE itself better, refines its latent space, improves its usefulness for downstream tasks.
And it generalizes well across different model sizes, architectures, settings, and achieves new SOTA results.
Pretty comprehensive set of advantages.
Definitely. So maybe the provocative thought to leave people with is, what does this mean for the future of building these models?
Right. If end-to-end is now truly feasible and beneficial, could we design architectures differently from the start? Maybe ones where the VAE and LDM parts are even more tightly integrated.
Or maybe apply similar end-to-end alignment principles to other areas, like video generation, audio 3D. Could we see similar speedups and quality bumps there?
It certainly opens up possibilities. Makes you wonder what other bottlenecks might be unlocked by finding the right way to train components jointly.
Absolutely, lots to think about. Well, if this has piqued your interest, definitely check out the full paper. The link's right there in the abstract. end-to-end-diffusion.github.io.
Yeah, dive in, see if these ideas spark anything for your own work.
And let us know what you think. It really feels like REPA-E has opened a new, very promising door for generative AI. Thanks for joining the deep dive.